Hello everyone, welcome to the first part of our deep dive into embeddings. Today we aren't going to write any code, we're not doing any calculus. Today is just about intuition. We're going to answer a fundamental question in machine learning. If you want to turn words into numbers and you want those numbers to actually make sense, how do you do it? We're going to move from a world of chaotic discrete symbols to a world of meaningful continuous vectors. Okay, so let's start with the problem we face in the real world. Imagine we're building a movie review system. We want our neural network to read a user's review and tell us if it's positive or negative. The review is the film was great. Here's the issue. The neural networks are mathematical engines. They do multiplication, addition, and calculus. They cannot read, so you cannot feed the string GREAT into matrix multiplication. So we have to convert this text into numbers, but, and this is the crucial part, how we convert them determines if our model is smart or stupid. Okay, so historically, the simplest way to do this was one-hot encoding. We take our vocabulary, let's say 10,000 words, and assign every word a unique ID. So great might be word number 4, awesome might be word number 500, for example. To represent the great as a vector, we create a massive list of zeros everywhere except for a single one at a specific index. We have 1000 indices representing like each word, for example. This is a discrete representation. It's mostly empty space, so we have only one assigned value, 1, the rest is zeros. It looks simple enough, but this approach has a fatal flaw. So here is the failure. In one-hot encoding word, every word has its own like island. Mathematically, these vectors are orthogonal. They are right angles to reach each other. So if you calculate the distance between great and awesome, it's exactly the same as the distance between great and terrible or awesome and terrible. So the vector for great knows nothing about awesome. To the computer, they are as different as cat or table. This means if our model learns that great is a positive word, it learns nothing about awesome. It has to start learning from scratch every single synonym in the dictionary, and that is incredibly inefficient, of course. So here enters the hero of our story, embeddings. Instead of a massive list of zeros, we represent a word as a compact list to real numbers decimals. This is called a dense vector. Let's look at our example. Great becomes, let's say, 0.9 to 0.88. Dad is represented by this vector, 0.15, 0.48, etc. Mom represented by this vector. These aren't like random IDs anymore. These are coordinates in a continuous vector space. We have moved from treating words as isolated symbols to treating them as points in space. It's better to visualize it using a scatter plot. The numbers in our vectors are simply x and y coordinates in this graph. When we plot our movie words, negative or positive sentiments, something magical happens. You can see how great and awesome, excellent, fantastic are almost on top of each other. They are clustered here. And almost in the opposite direction is the negative sentiment or negative words. They are also like clustered together. By using embeddings, we have physically separated the positive concepts from the negative concepts in this mathematical space. So this brings us to the core theory of embedding. Meaning is distance. Words that have similar meanings are closer to each other. In this space, we measure similarity using geometry significantly metrics like the distance or the angle between 2 points. If the distance is short, the words are semantically similar. If it's long, they are unrelated. So when we ask, does the computer understand that great is like awesome? The answer is yes, not because it knows English, but because the distance between their vectors is tiny. And this is the key phrase that we need to learn. I will repeat it. Does the computer understand that great and awesome are similar or synonyms? The answer is yes, but not because it knows English like we as humans do, but because the distance between their vectors is tiny. So you might be wondering, why do these specific what do these specific numbers represent? What does the x-axis mean? In a perfect world, these dimensions might represent clear concepts like positivity or intensity. For example, let's say grade has like a vector of many numbers. Each number, let's say 0.92, which is close to 1, is high. Let's say this is the positivity axis. If this is the negativity axis, we would have a low value. So imagine like every number between the commas represents an axis. In reality, neural networks learn these dimensions automatically. They capture the latent features, hidden attributes of language that might be hard for us to label, but allow the computer to distinguish between the concepts. Okay, so we move on to the distributional hypothesis. So the question is, how does the computer know like where to put these points? Who told it that great and awesome belong together? It relies on linguistic theory called distributional hypothesis, which states you shall know a word by the company it keeps. So we look at sentences like the acting was great, the acting was awesome, was fantastic. Because these two words fit perfectly into the exact same context, the computer assumes that they must have similar meaning. So we don't manually type these coordinates. We let the neural network learn them, of course using backpropagation, loss function, etc. We set up a game for the computer, often called self-supervised learning. We show it millions of sentences with the word missing, and we ask it to predict the blank. We can give it the whole of English Wikipedia, all of the I don't know, English dictionary. Like we give it the phrase, the acting was, and It should predict the next word, and of course, at first it would have like very low accuracy or would make many mistakes, but then it should learn the pattern and assign a vector to each word. So the structure of the space emerges automatically from the prediction task. Okay, why do we care? Why would we go through all of this trouble? Because of generalization. Going back to our movie review system, suppose we train our sentiment model only on reviews containing the word great. Later, a user writes, the film was awesome. Even if our model has never seen the word awesome during training, it looks at the vector space. It sees that awesome is right next to great. Therefore, it treats it the same way. It predicts positive sentiment correctly. The model has learned to handle unseen data by understanding relationships. Um, okay, now for the multi-model embeddings, this concept isn't limited to words, obviously. We can embed anything, images, audio, products, or even users in a recommender system like Netflix or Amazon. We create an embedding vector like for you, the user, and an embedding vector for every movie. If the user vector is close to the, let's say, Toy Story vector, in this high dimensional space, the system recommends it. It's all just geometry. So to summarize, um, discrete encoding like one-hot encoding are isolated and fail to capture meaning, but embeddings are dense continuous vectors that capture semantic relationships. Um, Meaning is defined as geometric proximity. Similar things are close together. We learn the structure by looking at the context, like the company or neighbors that word keeps. So we now understand the theory, the what and the why. Uh, so how does the neural network actually update these weights? What does the architecture looks like inside? We're going to see into that in the next presentation, where we're going to open this black box. We will look at the specific architecture of word2vec, the weights, and the dot products that make this learning possible. So I'll see you there. Thank you for watching. Please like and subscribe.